Thank you, Tim. It's a pleasure to be here in Campinas. In Schlumberger, we have several graduates from Unicamp. This is my first time here. I'm really enjoying the visit and appreciate the opportunity to follow up on the excellent presentations by Tito Bonagamba and my colleague Martin Hurlman this morning. So, since this is a physics forum, I thought I'd give you a little bit of an overview of the oil industry and sensor development in terms of the types of measurements we do. Like many things that we kind of take for granted that actually we think originated in the Western world, the oil business actually goes back to ancient China. The reason we know that date is exact is because the emperor taxed the salt that was being produced from wells that were drilled. And what they had discovered was if they drilled a little bit deeper past these sandstones that had salt water in them, they would find oil and gas, and they could use the oil and gas to fire burners to precipitate out the salt, and then they would sell the salt. And so the salt was taxed, and it entered into the records. And the next historical reference to the oil industry goes back to travelers in the Middle East, noticing the oil industry related to the seeps in Persia in particular. Marco Polo wrote about that on his travels. And the first oil well that was drilled in the US by Colonel Drake in 1858, just before the big Civil War. Colonel Drake actually worked on the railroad, and they think that he found out about drilling techniques from the Chinese railroad workers. And there was actually a salt industry already well established in Pennsylvania and Ohio that were using drilling techniques just like the Chinese were, going back almost 2,000 years. And earlier somebody was asking about fracking. If you remember, in the 1860s, that's when the US Civil War occurred, so there were big improvements in explosives, etc. And that's when fracking began. The first patent for fracking goes to 1865, where they started using nitroglycerin to enhance oil production in the well. So the first well drilled in the US was 1858. There's also evidence that a well was drilled in Canada about the same time, and also in Poland. And then they started to drill offshore in California just before the turn of the century. And then in the early 1920s, the Schlumberger brothers started developing prospecting technique based on surface EM to look for ore bodies, but also to map oil fields. And then they tried putting a sensor on the end of a wireline. You can see an early wireline logging truck from the 1930s. And that's where the wireline logging industry began. So the first sensors were electrical. In the 1930s, they discovered what's known as the spontaneous potential, which essentially looks at the potential between shale formations and sandstone formations. And they discovered that was a very good technique for seeing permeable sand beds. Then there was a big boom in Texas. They started drilling offshore US Gulf Coast. And that's when Schlumberger Dahl Research was established. World War II had broken out, so we'd moved our offices from Paris over to the US. And Henri Dahl, who was the scientist the research center is named after, he was using some of his ideas based on induction to come up with an improved mine detector that the US government was interested in. So that also facilitated the move to the US. He was one of the very few non-US scientists working for the US defense industry then. And also with, of course, World War II, there was a lot of interest in nuclear technology, and MIT was heavily involved in nuclear development. And that led to the development of neutron logging tools and gamma density logging tools, and shortly afterwards, sonic logging tools. So these dates here are when the technology was commercialized, when we actually started using it. Usually the R&D would begin about 10 to 15 years before that. And you can see about the same time the first NMR log came along. Now Martin gave a nice overview of the different types of NMR logging. We'll look at that a little bit later. And probably the most recent development is now that we acquire NMR data while we drill, not just from wireline logging. So once the well is drilled, we go out with the wireline truck, or we have an offshore rig, and we run tools that look like this that will fit down the borehole. Nowadays, we also can take that same data while drilling, and just most recently, we have mud logging devices that look at the cuttings that come from the wellbore, and we actually run NMR on those. So just in terms of the development, go from 1968, the first simple NMR tool that looked at a free induction decay, all the way to these newer tools where we can actually look at diffusion, not just T1 and T2, and we can do it both while drilling the well or afterwards logging it with wireline. Here we see the different options. This is the type of tool that's used in the pre-salt today. It's our smallest NMR tool. It has a very focused sweet spot right here. But we have another more complicated tool that uses actually a gradient that allows us to do diffusion measurements. Earlier there were some questions about how we can tell if pores are connected. One way to do that is through diffusion. And then we have the logging while drilling tool. And the big challenge here is we must keep the tool well centralized in the borehole. Any motion will affect the resonant area, etc., so we can get artifacts if the tool is not well centralized. There were some discussions about the difficulty of logging horizontal wells versus vertical wells. This is one of the big concerns for a horizontal well, keeping the tool centralized. So if we look at the different applications, and both T2 and Martin mentioned a lot of these, the fundamental response is presented as this T2 distribution. And when you look at these, you think the large pores are out here, the small pores are down here. But you also have other artifacts. If you have heavy oil, it will show up down here. If you have light oil, it will show up here. If you have gas, you'll lose some of the amplitude. So the key to interpreting these T2 distributions is to have a little bit of an idea whether you have heavy oil, water, gas, etc. And that's where we use the other log data, the density, the neutron log, to help with that. The neutron log in particular looks at the hydrogen index, which gives you an indication of oil and water, but if it's gas, you have a lower hydrogen index, so that helps you understand if you have gas. So we use the other sensors to help sort these things out. But where the NMR really can help is in estimating the permeability. When you consider the new wells that are being drilled here in the pre-salt, the best ones can produce at over 30,000 barrels a day. And that's an incredible flow rate. There's only a handful of wells in other parts of the world that can produce like that, and they're all from the Middle East. The great wells in the US Gulf Coast now, they only produce about 10,000 barrels a day. The average well in the Middle East is probably about 5,000 barrels a day. So to get flow rates of better than 10,000 barrels a day, you need permeability of 1,000 millidarcies or 1 darcy to get that kind of production. If you have 100 millidarcies, you're going to get production between 1 and 5,000 barrels a day, 1,000 to 5,000 barrels a day typically. Now the problem in the pre-salt in Brazil is a well that only makes 5,000 barrels a day is not sufficient to pay the costs. You really need production ideally better than 20,000 barrels a day. So the major challenge for us in terms of interpretation with NMR here in Brazil is, can we use the NMR to tell when we're going to get about 5,000 barrels a day versus 10 to 20,000 barrels a day. There were some questions earlier about stimulating the well, fracking, etc. So typically, if your permeability in carbonates is better than 10 millidarcies, you would acidize with HCl. If it's less than 1 millidarcy, you would have to fracture the well. If it's between 1 and 10 millidarcies, you would typically, you would combine the acidizing with fracturing. So all the tight gas that you read about now, the shale oil, etc., that's all well below 1 millidarcy, and you have to frack it. So in addition to all these other uses for NMR. The other one that we're discovering is important here in Brazil is wettability, and that refers to whether or not the oil is in contact with the grains or the water is in contact with the grains. And we'll look at that in more detail soon. So in terms of the Brazilian pre-salt carbonates, there's a couple of things to keep in mind. They're in 2 kilometers of water, and on top of that 2 kilometers of water, there's 2 kilometers of salt. Or below that 2 kilometers of water, you have 2 kilometers of salt. Now, when you drill through salt, if you use a water-based mud, you will dissolve the salt and you'll have a lot of problems with the hole collapsing. So typically, when you drill through salt, you like to use an oil-based mud. Now, since these wells are about 200 kilometers offshore, they like to keep with oil-based mud even when they've drilled through the salt and then start drilling through the pre-salt carbonates. If they were to change to a water-based mud, and it's easier to drill with water-based mud and carbonates, you can drill faster. So one of the big problems with the pre-salt is it's very slow to drill. And if you could switch to water-based mud, you could probably drill quicker. But because they're 200 kilometers offshore, they would require a tanker to offload that oil-based mud, another tanker to bring in the water-based mud. So it adds quite a bit to the costs. Now, these carbonate formations in the pre-salt, they're about 18,000 feet deep. That means they're fairly high pressure. They're somewhere between 8 and 10,000 psi typically. But they're not that hot. They're only about 60 to 80 degrees C. So that cool temperature helps ensure that the oil is still good quality. It's not been degraded like other high temperature formations you might find. And so this high quality oil is important because it has very similar properties to the oil-based mud filtrate, and that has a big impact on how we interpret the NMR. Now, as Brazil was separating from, or Latin America was separating from Africa about 60, 80 million years ago, a series of very saline lakes were being developed as the continents split, and these lakes were so saline, the only thing that could survive in them was blue-green algae. And when the blue-green algae dies, it sinks to the bottom and forms these microbial carbonates that are called stromatolites. They're essentially layers that can extend for kilometers of blue-green algae turning into hard calcite. And as the blue-green algae keeps forming, sinking to the bottom of the lake, it also traps carbonate grains and other sediment. And so you get these sequences of hard calcite layers with trapped sedimentary material in them. And in time, it gets buried deeply. And if you have a fault and you have hot water coming up through the vents, that hot water can dissolve the carbonate grains but leaves the hard calcite from the ancient algae. And these formations known as stromatolites can have very good porosity, very good permeability. But the hot water that comes up from the vents can also bring silica that gets deposited as quartz. So you have very complex lithology. The white spots here, usually this is quartz. This is from a stromatolite from the pre-salt, from a paper by Petrobras. And it's a mixture of calcite or limestone and dolomite and quartz. So it's a fairly complex lithology. That means if you use traditional devices like density or neutron, you have to correct for the type of mineralogy or lithology. But NMR, because it just responds to the hydrogen protons, it will give you a porosity independent of the mineralogy. So the first application that Petrobras noticed using NMR in the pre-salt was it gave it the most accurate porosity reading. And that's important because the first wells that were logged in Tupi Field didn't really show that high porosity compared to, say, the great carbonate formations in the Middle East. But looking at the NMR T2 distributions, they could tell the permeability was very high, and that's why they get such excellent flow rates. So NMR is primarily used for the porosity indication, but also to estimate the permeability. And to enhance the ability to estimate the permeability, we take advantage of the fact that these carbonates are also oil wet. The carbonates in the Middle East are actually more water wet. The water clings to them more strongly than it does to the carbonates we have here. And when formations are more oil wet, they're much more resistive. It's more difficult to use resistivity logs to determine water saturation. So using NMR also is a nice technique for separating the water from the oil. So the key to getting this pore size information from NMR, Tito showed this equation earlier, is T2 is a function of the T2 of the fluid in the formation, but also the size of the pore. This would be the radius of the pore. And this would be a constant here. 3 if it's a spherical pore, 2 if it's cylindrical, and 1 if it's a planar pore. And the properties of the bulk fluid are what can have a big impact when you're trying to interpret NMR in these type of formations. So this would either be the native oil, the reservoir oil in the pre-salt formations, or it would be the mud filtrate. And so there are 3 principal ways for characterizing carbonates. You can do it based on the size of the grains, you can do it based on the size of the pores, or you can do it based on what we call the pore throats. That is what connects the pores. So if you look in any of the literature for carbonate analysis, you'll see references to these different techniques here. And so with NMR, the T2 distribution is considered a proxy for a pore size distribution. And the way we get pore size distributions in the lab is to use a technique known as mercury porosimetry. This is an example of mercury porosimetry. What you do is you inject mercury into the core, and based on the pressure required, you can tell the size of the pores. And so they histogram the size of the pores based on that cumulative pressure response. So these are the large pores. We call these the macropores. These would be the mesopores, and these are the micropores. And if we look at a T2 distribution from the same core sample, you can see this correlation between T2 and the pore size distribution for this sample and also for this sample down here. This is an example of a ×10 magnification visible light microscopy from a thin section taken from a core. And the blue is epoxy that's been injected into that thin section to show you the pore space versus the minerals that are non-blue. So to use this technique on NMR, there are 4 key conditions. Earlier, there were discussions about diffusion. Diffusion can influence where things occur on the T2 distribution. You want to ensure when you're using this technique that diffusion is not an issue. So the way we do that is we log with a very short echo spacing, so there's not sufficient time for diffusion to be in effect. The other way you can do that is with the logging while drilling tool, you have a very low gradient, so that also minimizes the diffusion effect. The other key condition is you want to ensure that any water, oil-based mud filtrate, or the reservoir oils in there have a T2 bulk of at least 1 second or longer. And the pre-salt oils, the oil-based mud filtrate, and water all have a T2 bulk much longer than 1 second. T2 also mentioned how we can use diffusive coupling to look at whether pores are connected. We can do that in the lab, but it's still very difficult to do downhole. So we really want to ensure that diffusion here or diffusive coupling is not an issue. And the fact that these reservoirs are oil wet actually helps, because the water which remains in the small pores now will not have any diffusive coupling with the oil that's in the big pores. And then the other key requirement is we want to make sure that the pore fluids are actually wetting the grains, so you get this surface effect here that gives us information about the pore size. So if you were to plot that equation with T2 on the y-axis and the pore radius R on the x-axis, you see you get this nice relationship between T2 and pore size up until you get to large pores. So once this gets big, then this term starts to take over. And here you're seeing the trends for a T2 bulk of 1 second, 2 seconds, and 3 seconds. So you still have information about these large pores, but it's not as nicely defined is in this range. So when we have this situation, predominantly micro and mesopores, we use a equation based on T2 squared, which is essentially saying the radius squared is controlling the hydraulic properties. So that's what determines the permeability. So it's important to remember we don't actually measure the permeability with NMR. Permeability is a dynamic measurement. You have to actually measure the flow. But we're inferring it based on the pore radius and the fact that there's some kind of connectivity between pores. Now, when we get into the large pores and we lose that relationship between T2 and pore size, we can still estimate the amount of large pores. We can't tell exactly their size, but we can estimate the amount. And so we use a different equation where we use the ratio, the large pores essentially divided by the smaller pores. And this was a technique pioneered by a Chevron researcher, Turk Timur. And it's known as the Timur equation for estimating permeability. So here it's the ratio of large pores to small pores. Here it's more the square of the pore size. So you have these two techniques for determining permeability. And the key to using these techniques in the Brazilian carbonates is to understand when you apply one, when you apply another. So we did a series of measurements in the lab. Here you can see Paulo Federico. He's one of the Petrobras researchers at the time, a few years ago, using some lab NMR equipment at the research center back in Rio, SEMPS, which is just down the road from our research center in Brazil. And in addition to the lab NMR equipment that Petrobras has bought, they've also helped a lot of Brazilian universities buy lab NMR equipment. Tito gave you a nice presentation earlier about USP, and then there's at least 4 other universities that we collaborate with through Petrobras on various projects. And so what Paulo Federico was actually measuring here is the T2 response of the oil-based mud filtrate, and you can see it's about 2 seconds. That implies it's got a viscosity of about 0.5 centipoise. So it is important to measure the mud properties. Sometimes we do it at the rig site, but normally we will try to get a sample and measure it in the lab. We can heat it up to downhole temperature in the lab. We don't necessarily raise it to downhole pressure, but we do heat it up to downhole temperature because that affects the T2 response. Then we take cores from the pre-salt and we saturate them with salt water or brine, and we measure them. And you can see this response here with the brine-filled cores. These would be the large pores, the mesopores, and the micropores down here. And then we take that oil-based mud filtrate and we centrifuge it into the core and remeasure it again. Now, when the oil-based mud filtrate is in there, you can see that things shift from here out to here. They shift by a factor of 3. And there's a couple of things that cause this. One, the oil-based mud filtrate is displacing that water as we centrifuge it in. And the oil-based mud filtrate, the hydrocarbon molecules are much bigger than the water molecules. So the surface relaxivity effect is weaker, and that means the T2 has a longer time. And so that amount of shift can be interpreted as an indication of the wettability of the formation. If you know what a wet brine-filled formation looks like, and then when you put the oil in, then you can infer that as oil wet. If that oil-based mud filtrate wasn't wetting the grains, the response would still be out here. And this is what you typically see in sandstones. If you put the oil-based mud filtrate into a sandstone, it will stay out here because sandstones do a much better job keeping the water molecules clinging to them. Now down here in the small pores, they remain water-filled, so we never get oil-based mud filtrate in them. So we don't see any shift there, but you see this pronounced shift to the right to longer times due to the oil-based mud filtrate. So using the fact that both the water and the oil-based mud are wetting the grains, we can use this equation to relate T2 to pore size. if we know where the water is, which is down here, we have this trend. Where we have the oil, we have this trend. And we keep in mind that the small pores keep water in them. The larger and the intermediate pores let oil in them. So when we mean oil wet, this would be the case here. If you had oil on top of water and you stuck a capillary tube in it, which is the equivalent of what you have in porous media, if that porous media is oil wet, then the meniscus will look like this. If it's water wet, it will look like this. And if it's neutral wet, it'll be at 90 degrees. So that contact angle is an indication of the wettability. And one way wettability is defined is if the contact angle is less than 90 degrees, it's considered water wet. If it's greater than 90 degrees, it's oil wet. So the small pores keep water in them. The meso and the macro pores become filled with oil. So the response actually looks like this when we relate T2 to pore size. And the last thing we do in the lab is we get the data from the NMR log, which is in green, and we overlay it from that same depth interval, and you see this nice correlation between the lab data and the log data. So we're using a lot of these lab measurements both at SEMPS and the universities to correlate what we see on the logging tools with what we see in the laboratory to better understand what's really happening in the formation downhole. And so we use this technique of porosity partitioning where we use the T2 distribution to divide it into the micropores, which will keep the water in place, the mesopores and the macropores. This is where you can get the great production. This is where you can produce in the thousands of barrels a day range. This is more in the hundreds of barrels a day range right here. And then there's another technique that we like to use to also isolate or indicate where the macropores are. And this is based on electrical image logs, which were also developed at Schlumberger research in the early 1980s. And here you have a very dense resistivity array that actually is measuring the conductivity of the formation. And so these darker zones, this is what contains the fluid. These whiter zones, that would be the hard quartz that we see on this core over here. This would be non-conductive, but these pores with fluids in them would be conductive. So you can evaluate the large pores using these image logs based on electrical response, or you can also make an image log based on ultrasonics. It's not as high resolution as the electrical image log, but you can still see where the Vuggy porosity is. So just to summarize, the main applications for NMR in Brazil is first of all to give a good porosity, because that tells you how much oil you can contain. And then we like to partition that porosity into the micro, the meso, and the macro pores. And we have two different transforms for evaluating the permeability based on whether it's dominated by micro and meso porosity or whether it's dominated by macro porosity. And we're working with Petrobras researchers. I see William and Bernardo up here. And one of the key things they're working on is when do you transition from one technique to another to come up with the best overall permeability. And then the other key application is this is an independent way of getting the oil volume versus the water volume to supplement other techniques based on resistivity logs. So we've got a minute or two.
Yeah, thank you very much.